Hello, welcome everybody to the Qiskit Global Summer School Commencement. Thank you so much for joining us. I'm going to give people a little bit of time to come in and get their setup going for watching the presentation today and also the panel discussion. And in the meantime, please go ahead, introduce yourself in the chat, say where you're from. It's really, really great to see all the interest and all the people that are here to learn about quantum computing and quantum machine learning. Let's see where all the people are from. I see someone from Vermont, from Zimbabwe. Oh, cool. Germany, Russia. This is really quite amazing. Italy, England, USA. Oh, awesome. And I see lots of familiar names as well. So for those of you who are joining us who did not participate in the summer school, my name is Amira and I am a researcher at IBM. And for those of you who were at the summer school, you're probably very tired of seeing my face because you've seen it for the last 2 weeks. But yes, this is it. This is the final stretch. And I'm very excited to go through this commencement presentation and the panel discussion. So, okay, it's 2 minutes past the hour, so maybe we can start. So firstly, congratulations to all the students that made it through these last 2 weeks. So again, just a reminder, the Qiskit Global Summer School ran for the last 2 weeks and it consisted of lectures and labs. And this was not easy. This was really quite an intense 2 weeks filled with lots of information thrown at you. So a massive congratulations and well done for persevering and getting through this far. I mean, this is really quite an impressive accomplishment. And if you have made it, just a big well done to you, because this is something that I think is quite awesome, especially if you're new to quantum computing and machine learning. This is really quite a feat. And something I want to highlight about the Qiskit Global Summer School is really just how global it was. The reach and the level of engagement was truly breathtaking. I mean, we had students, 5,000 registered students from over 111 countries. So really the diversity here in the school was tremendous. We had people starting groups in their native languages. We had people with no experience in quantum computing at all or with Qiskit. We had lots of learners, but also industry professionals, and just the geographies and the amount of diversity and different people that came together to make this school something really quite amazing. It was just a wonderful experience, and also to have a scientific event of this scale, I think, is something quite spectacular. So I wanted to just highlight that. And of course, this event and events like this, especially of this scale, are not just thanks to one person, right? It takes a whole community, a whole team, a whole driving force to really push this forward. And so here you're seeing pictures of the lecturers and also the core planning team. And I just want to say a huge thank you to everybody involved in putting together the content, the course, and also just making sure everything ran smoothly over the last 2 weeks. And in particular, I want to highlight one specific person, and I don't think anyone here will disagree with me on this. That this person was really the reason why the summer school was so successful, that ran so smoothly. And this I want to say a huge thank you from the bottom of my heart to Josie Kiss, because without her, everything would have fallen to pieces, undoubtedly. So this summer school was really so successful because of Josie and of course everybody else. But Josie did everything from making sure things like Discord servers ran smoothly, Q&A sessions were streamed, everything was just done very, very smoothly and very well. So thanks, Josie, and thanks to the rest of the team. And of course, the pictures that you're not seeing here, like a special thank you to, for example, the mentors that we have, the support team, the video team, and in particular, I just want to further highlight those mentors because they're also from lots of different countries, different time zones, and helped us so much in answering the questions from 5,000 students around the world. And we could not have done this without your support and your volunteering experience and help. And just, again, a huge thank you. And now I just want to quickly remind you of some fun times that we had. So thanks again also, of course, to the lecturers for the content. So every lecturer developed the content for their session, for their talks. And this was highly appreciated. And we had like some very fun Q&A sessions, question and answer sessions after every lecture. And the questions were beautiful. They were absolutely wonderful. And just the engagement again, and the community that we created when we did all of these things, was just, it felt like it felt like an event where we were all together. And this was just, I think, really, really fun and just very nice. So thank you again for the lecturers doing the content and answering the questions from all the students after every session. And also thanks so much to our ongoing and growing Qiskit community. So everybody who participated in the school and also those observing from the outside, part of the Qiskit and the quantum computing community. You're seeing some screen caps here of just some nice moments and posts that people posted about the summer school, but of course there were tons more that I would have loved to include here, but didn't have the space. But thank you so much, for all the positive feedback, all the wonderful memories, all the experiences shared. This was just really a wonderful thing to see, and to see it about, the field that you're in. For me, like in quantum machine learning, this is just, it makes me very, very happy to see that the level of interest and participation and excitement is just breathtaking. So thank you so much. And then I want to just quickly recap for those of you who weren't part of the school, just to tell you how much the students have actually gone through and what they've done. So like I said, it wasn't easy, right? It was quite a jam-packed schedule. So in the first week, and this really did not assume a lot of technical knowledge. So this summer school catered to people from all kinds of backgrounds, from all kinds of different experiences, and you didn't really need to have a lot of technical knowledge. And so in the first week, it was really spent getting people up to speed with quantum computing. So the first 3 days were about the basics of how quantum computing works, how our devices look, like our actual quantum computers and like the noise in them. Then on Thursday, we went into classical machine learning, understanding the basics of what machine learning actually is on normal computers. And then on Friday, we finally peeked into the idea of marrying these two concepts of quantum computing and machine learning. And we looked at a little bit of what it means to do quantum machine learning. Then in the second week, I think this is where things got a lot deeper. So we started going into what it means to do machine learning tasks with a quantum computer. So what quantum machine learning actually means. And we looked at things like quantum support vector machines and parameterized quantum models for classification. On Thursday, we dived into hardware, so actually understanding quantum computers for machine learning tasks. And then today, we concluded with some advanced quantum machine learning algorithms and also just a lecture on the future of quantum machine learning. Like, what can we hope? What can we do with it? And hopefully, that got you thinking about some very nice questions for today's panel discussion, because that is, of course, the topic that we're here to listen about, is the future of quantum machine learning. And in the beginning, when we opened the summer school, I put up this slide because I wanted everybody to kind of ask these questions or have these things in mind of whether they will be able to take this away after the 2 weeks. And hopefully the answer is yes, they can. So this is what we wanted students to really walk away with, was the ability to discern between what is hype and what is actually doable in today's time, with this idea of quantum machine learning, with this idea of taking quantum computers and trying to understand how can we use them for machine learning tasks in a useful and practical manner. And so the idea of like understanding the limitations as well as the potential of quantum machine learning, these are all the things that we wanted people to understand and explore. Also implementing algorithms and applications with simulators and quantum computers, and also just to get an overview of what's actually going on in the research, because it is a very fast-paced environment and a rapidly changing field. And so hopefully we did a decently good job on getting you up to speed with what's going on in the field. And lastly, I just want to remind those of you who are students watching this that the deadline for the lab submissions has been extended to next Friday. And also the Discord server will be closing on August 6th. But don't worry, because of course you can still join the Qiskit community via Slack and Twitter and so on. And so we can still continue to share information and resources on there. So please go ahead and and join Slack, join Twitter, and get in touch with us and continue this excitement and this discussion around quantum machine learning. Okay, and with that, I can finally introduce our wonderful panelists. So I am super, super excited to be here today to be talking about the future of quantum machine learning with some of the greatest minds in the field. And for me, this is like a dream come true. So I'm very, very excited to do this. And I want to introduce each of the panelists. So the first is Kristen Teme from IBM Quantum. Kristen is known for a bunch of quantum computing things like error correction, and then also, of course, quantum machine learning. In fact, Kristen is amongst one of the first researchers to propose this idea of quantum support vector machines, and this is really, you know, one of the most promising ideas that we hope will see an advantage in quantum machine learning. So Kristen has really been quite influential in the field of quantum machine learning, as well as other fields in quantum computing. And then we have Ewan Tang. So Ewan has a very interesting background as well. She enrolled at the University of Texas at Austin at the age of 14. I think she's also very well known for dequantizing one of our most, what we thought was one of our most promising quantum machine learning algorithms. She came around and said, actually, no, it's not. We can do it pretty well on a classical computer. So that was pretty impressive and pretty awesome. And so Ewan comes with a very unique perspective. So I'm very excited to have her on the panel. Then we have Aram Harrow from MIT. And Aram, of course, is also very, very well known in quantum information theory, quantum computing. For those of you, you know, who attended the summer school and just are familiar with quantum computing, there is this very famous HHL algorithm. That first H is for Harrow, so you know what's up. So I'm very, very excited to have Aram join us as well. And last but not least, we have Maria Schult from Xanadu. And Maria, I think if you Google anything quantum machine learning, it will either be her work, or it will either heavily cite her work. So she is one of the formative minds in quantum machine learning. So it's really quite an honor to have all of these panelists together to discuss the future of quantum machine learning. So let me stop sharing my screen. And now we can finally begin the discussion and the panel. So I want to just start with a very broad question, which I think is on the mind of most people. And it's just around, what do you guys think will be the most promising application of quantum machine learning? So maybe we can start first with Kristen. So Kristen, can you tell us, what do you think will be the most promising application of quantum machine learning?
Right. So I mean, there are many ways you could approach that question and think about it. And so it's, at this point, I'd say it's a bit difficult to exactly pinpoint a given application that would be of value, or whatever it is that you declare to be of value. There are, however, a couple of ideas that are emerging in the field, which are sort of interesting. And so in the broader sense, some of those things that are emerging are basically, you could sort them towards a direction of saying, well, you could use a quantum computer to try to make classical machine learning protocols go better, and in the hope that maybe there's something a quantum computer could do. And so typically that early on falls into sort of optimization type questions, for which we know that quantum computers can formally at most offer sort of a polynomial speed up in that setting. Then there are other ideas that are basically where you hope that there are certain features that you can use a quantum computer for, that give you, basically where the quantum computer gives you access to compute certain properties of the data that you would like to classify. And so those were the ideas of basically going along those feature space methods and kernel methods and so forth, where you could say, in this setting, you could use a quantum computer to gain some form of an advantage. And so there, it's more about actually extracting the valuable features from the data, as opposed to the actual learning part. And so what I think, so personally, I'm sort of in favor of that. And so that's one thing where I hope to see some early applications and value being delivered in some sense. Right?
Cool, perfect. Yeah, thanks. I think, yes, you've given us a very, I think, a broad answer. And I think more the people are wondering, like, specific fields that could be impacted, right, with promising applications of quantum machine learning. So I see people in the chat are like asking, could it be used for healthcare? Could it be used for finance and so on? So I guess that's yeah, a little bit more specific, right? Yeah.
Right. So so the question is, in the end, is basically, I think where a quantum computer could help you is if you were able to reduce your specific problem to an abstract math problem, right? So if you find that problem somewhere in healthcare, if you find that problem somewhere in finance, or if you find that problem somewhere in, say, I don't know, classification of physical experiments say on the LHC, or classification of many other things, then yes, that's where you would want to look. What I wouldn't want to do right now is probably, I wouldn't jump in and say specifically, well, this is going to change how we do finance forever, or this is going to change how we do certain other aspects forever. So I wouldn't want to go and specifically pinpoint a given field, but sort of what I'd expect is basically typically problems where you have a lot of math that can be exploited.
Okay, perfect. And yes, I want to remind. Yes, go for it. I was just going to say, please, panelists, feel free to add and interrupt each other. Go for it, Ewan.
So I was I was under the impression that like there is like the most promising sort of direction would be sort of machine learning on like quantum systems. Like this seems like a straightforward. This sort of makes sense to me. But are you saying that this is like not true? That maybe like the applications are not like applications to like measuring quantum systems are like less promising then, or like as promising, or is it just like wherever you can find it and we don't have any idea of where you could find it or any sort of guess?
Sorry, to who is this directed, the question?
I guess to you.
To me? Okay, cool.
Yeah.
No, so I think I agree. I agree with you that it's a very natural place to look, because you already have data that is coming from some quantum process, and you could hope that that you could use a quantum machine learning algorithm to basically classify that data better. So yes, I think a good example is exactly you run an experiment on the LHC, and there's a lot of data that's coming out of this machine. It's very difficult to classify data that's coming out of the machine, and so you could actually then wonder about, is that a place where you could insert a quantum machine learning method where certain aspects of the learning algorithm are essentially done in a quantum computer and extract valuable information there. So yes, I think that's actually a very good initial suggestion. I agree.
Can I also voice my opinion? So I already warned Amira that I will be the devil's advocate, because a panel is not nice if there's no one like, you know, saying a bit of like nasty truths that might also not be totally true, but just like taking that role. And I would say, so define what, I mean, scientists always have to define first the question. So what is application? And I guess the first level of definition there is like, are we talking about commercial applications like healthcare and all of those things? And then I think none. If you have an application like that, take a classical machine learning algorithm. And that's probably true for the next 10, 20, I mean, no one wants to do like predictions into the future, but it's very, very unlikely that this is like soon to be happening. Then the second definition would be like the more scientific one, the more like, you know, generous one towards our purposes, and their application is maybe a problem. And then is the question, okay, what is a problem where you could use quantum machine learning and this like speeds up things? And I would say these problems are very, very untypical for machine learning. They are very structured. You know, if you think of quantum algorithms, there's often like Grover search and so on and so forth. There's something periodic going on, quantum Fourier transform, something interference is used on something that's very, very structured. And usually you try to find patterns in data, but data is something that's messy, that's unstructured. So also there, I would say we know that there are some problem classes constructed where something interesting is going on. They're very important for us theoretically, but also there, I'm not entirely sure where the relevance lies. And so maybe we have to break down this idea of application even more, make it more general, and say like, just which kind of settings does this become interesting? And I think that question has a lot of answers, like in terms of how we can combine something like energy and physics, and how we can understand physics principles as regularizing in machine learning. And these kind of meeting points, I think there's a lot to come. And maybe after those, we can go back down the application route in 10, 20 years and say, this is now the commercial one. So that's, yeah, maybe the bit more negative or conservative view.
Yeah, I think I agree with a lot of what's been said. I mean, I think Maria's pessimism is I think we're all probably share some of it. I think that you know, one thing I would emphasize is how much we do not know. So just like, let me just say the levels of things we don't know. For classical machine learning, we don't know generally, you know, when it's effective. If we had much faster classical computers, I don't think we know to what extent that could improve our models, right? If you could just take the training time down to 0 for our deep neural networks, I'm not like the machine learning experts I've talked to don't know to the extent that could improve things. And so just on the classical side, there's a lot of uncertainty. And then on the quantum side, I partially agree. I think this panel is more fun if you disagree a little bit. So I partially agree with Maria that it's the structured problems where we found quantum speedups, but at some level, that might reflect the fact that only structured problems have quantum speedups, or it might reflect the fact that this is a theoretical, quantum algorithms have mostly been a theoretical enterprise so far. We haven't, until very recently, had quantum computers where you can just run the things and find out how well they work. If you look at classical algorithms like the Metropolis algorithm, this was an important algorithm starting in the late 1940s, right? And it was only very recently proved that it actually runs in polynomial time on, let's say, the 2D disorder, 2D icing model, right? It was only recently proved to work, and nevertheless, people ran it. And so with quantum computers, there's very little we can prove, and maybe when we try things empirically, we'll find that they work somewhat better. Just to be a little more concrete, and this also kind of illustrates some of the issues at hand. So one of the exponential quantum speedups is for this super contrived problem where you have two binary trees and then you weld them together in the middle, and then you traverse from one end to the other one. And along with a student of mine and a former postdoc, we've been thinking about generalizing this to more disordered graphs. So like more general families of graphs. You have a quantum walk, which is a generalization of a classical random walk. You should find that there are many, many cases where you can traverse these much messier graphs exponentially more quickly. It's still not into the realm of practical problems, but we're hoping it comes closer. And then you have to think like, how far do you have to go to like make that into a practical problem? This is like what Kristen was saying. You have to find some kind of mathematical structure in your biology problem or your finance problem. So somehow this hard problem in, I don't know, protein folding or whatever, you have to represent as traversing some exponentially large, bumpy, high-dimensional landscape. And you hope that that has the structure that's amenable to speed up via these quantum walks. But we're probably not going to be able to even characterize this exponentially large landscape. And even with more research efforts like the one that I've been working on, we're only going to understand still only some of the cases where quantum walks can do well. So, I would temper our pessimism with a giant amount of uncertainty that there is room for exponential advantage where we really, and there's just tons of stuff where we don't know. And I think one thing that's kind of exciting, especially about things like this summer school, is the idea of people from all these different fields. I don't know about the computational problems in finance or medicine, things like that. Thinking of ways of trying quantum computers, quantum kernels, quantum machine learning methods, whatever, on their problems. And maybe most of them don't work, but I hope trying a variety of things we'll start finding things that we didn't expect. So I think in general, there's a lot of things where we don't know, but there's room for something positive. And the case where we're more certain, I think, is machine learning related to modeling quantum systems. I think.
So maybe then one can specify. So I really like this very much, and we have this absolute selection bias in everything we say and state at the moment towards theory, obviously. And maybe one can say, maybe this is another definition of application. Do you want an application where you have a provable advantage? And I think then you can be a bit more pessimistic. And then if you drop this provable advantage, you open up 99.9999% of all the problems that we're actually not even looking at now. Yeah.
Yeah, like if you want provable classical machine learning, what do you have? Linear regression, right? And a lot of things we do don't.
That's the cool part.
Kernel method, kind of, but you don't know that there's like a good, like SVM. You don't know that there's going to be a good hyperplane, right?
Well, in some instances you do. So there are some examples where you could construct something, but so for a relevant practical problem where you exactly given the data and don't know anything about the data that you exploit, then I completely agree with you that you don't know, and you just run it and then hope that the learning curve looks good in the end, right? But I guess you could construct, like there's half-space learning examples where you could construct that provably, but I mean it wouldn't necessarily be be something that you would encounter naturally. I agree.
This is actually a very nice segue into a question I wanted to ask you, Kristen. So why is it so hard to find good like universal quantum kernels, given that classically we already know, of kernels that work quite well in general, right? Like these Gaussian kernels and so on. And maybe just for the benefit of the audience, if you could just quickly in like a few words remind, some people who don't necessarily know what a quantum kernel is and what it's used, what we're trying to do with them, right?
Right. So the basic idea is basically that there is in classical machine learning and many other parts of statistics, there's a trick which is called the kernel trick, which essentially does the following. It allows you to use allows you to use linear statistical methods for classification, for regression, for many other problems in a nonlinear setting by essentially first applying a feature map that maps it to a very high dimensional space. And then because that is sort of painful and rather unpleasant to have that in a very high dimensional space, it allows you to sort of, the kernel trick is then the observation that it's often only necessary to actually know inner products in that feature space. And that's a very, very commonly used trick. It's in the context of classification. It's been used since the 90s, and it's actually been a bit older than that. And as far as your question goes, so the thing is, I think like a lot of the demand on what you would be setting on using a quantum computer to estimate such a kernel function as opposed to using a classical computer is so that you sort of have to have a justification of why you would want to use a quantum computer for that, right? And because if you could do something that's sort of very easy classically as well, you wouldn't want to go and waste your time using a quantum computer for it and so forth. And so I think that the hardness or the difficulty in finding good examples for that kind of problem relies on the fact that you sort of that you're in the setting that Aaron mentioned, essentially that where you want something where you can sort of formally justify of why you're doing what you're doing, right? But in a lot of practically relevant settings, it's sort of not really possible. So that's the thing. I mean, you could write down a lot of things, but you wouldn't know of whether they would do well or would do bad, or would do worse than a classical thing. So yeah, I think that's where a lot of the difficulty lies. So.
Okay, well, and that also I think is a nice segue to the question that I wanted to ask Ewan. So yeah, I think this interplay between like classical and quantum algorithms is quite important. So Ewan, I know given your your background and stuff, do you see any potential for quantum inspired classical machine learning algorithms, like similar to the algorithms community? So to phrase it differently, can a quantum view also help classical machine learning?
So I mean, I think the answer is possibly. But certainly like the tools that I use to analyze the current quantum machine learning algorithms that exist are not necessarily tools that actually work in practice, because like sort of the current state of quantum machine learning literature is simply that we just try to aim for things that are provable because this is all that we can do. We can't like run quantum machine learning algorithms at full scale quite yet. And so in fact, like the techniques that I use to show to demonstrate sort of these provable like to sort of disprove or show barriers for exponential speed up for quantum computers actually don't perform that well in practice, simply because these sort of, I mean, they're sort of designed to give provable guarantees, and there hasn't been like I guess a ton of effort to sort of see whether or to hone them for practical use. And so I think certainly like one could find inspiration from quantum computing for classical machine learning. I mean, certainly this is done in the sort of optimization setting. This quantum inspired optimization is definitely something that's big. I'm not informed enough to say whether it works or not, but it's certainly something where ideas from quantum physics sort of become useful or become a nice perspective. But I think in terms of like classical machine learning, it's sort of a slightly different question, and it sort of relies on intuitions that are something that I guess are going to be something I can't really speak to, but yeah.
Yeah.
Mm-hmm.
So I guess the answer is always conservatively it depends, right? So possibly, but yeah, we'll see. I don't know, Maria, do you have something to add? So the question was, I remind you, do you think quantum computing can help classical machine learning in general? So maybe we can get some ideas on what we do.
Yes. So actually, Erin, I really like that notion of like, just know that the dequantized version of these algorithms, they are made for a certain purpose, right? They're made for this whole theory part. Yeah. Okay, so let me continue with my, slightly maybe different viewpoint. So I'm kind of like started a couple of years ago to take a stance that's maybe a little bit unpopular in quantum computing communities. And when I tell students, they're often shocked, and I also like shock myself a bit with it. And that is, maybe speedups are actually not important and interesting. And so why this is obviously very controversial is that we are driven by, I don't know, this narrative of, we now have quantum computers, there's a lot of investment into it, and most of our researchers now work for companies, and we kind of need to make this work. So we're kind of a little bit a mixture of sales rep and engineers and researchers, and it's a bit strange. But in some sense, the question of like speeding up classical machine learning has already a lot of really tricky problems. So the first one is, what's your notion of scaling, or your input to your algorithm is your data. So we're talking about data set size, right? So this is like what you want to scale with. And classical machine learning neural networks scale linearly in the size of the data, and they work well, as we know. So you have to kind of like speed up something that's already linear in the data. Now, at the beginning of quantum machine learning, people try to do something that's sublinear in data. And then you can start arguing, okay, but if my problem is take classical data and learn from it and give me a prediction or something, I have to take the classical data, which means I'm already linear in the classical data. I have to kind of load it and touch it and see it. Otherwise, the problem is completely differently defined. So I'm already in a regime where I have, in some sense, I mean, a very rough sense, optimal runtime. Now you could say, okay, but there are other interesting things. For example, there are these kernel methods we were talking about. They scale, unless you approximate, there are beautiful approximations out there, but if you do it like properly according to textbook, they scale quadratic in the number of data. So I can say maybe quantum computers could do this quadratic to linear reduction. But then a lot of discussions at the moment in the quantum community is maybe quadratic speedups are actually not enough because the constant factors are so big. So I actually myself wasn't really like super aware of the details of the argument. There's a very beautiful article on PRX Quantum from Jerry McLean and the Google team, explaining the background. And so maybe this is also not so interesting. So now we're back to really small problems that we cannot solve yet in classical machine learning. So we're already in a niche. So sorry, I spoke a bit long, but I wonder if this whole speed up question is actually not the essential one. I wonder if the important question here is, let's build infrastructure. Let's build the tools and the methods and the understanding and the mechanisms. Let's be like proper physicists. Let's create an icing model that generations of people can use to sharpen their thoughts on, and then let that whole like spin-off come later. So that's, what I would say about this whole, like, obviously everyone asks you, like, is quantum computing better? And then I would say, I don't know about this question, Yeah.
I would love to hear Aram's opinion on that, because I know we had a very brief discussion about exponential speedups and this idea in machine learning at a quantum machine learning conference not so long ago. So I don't know, Aram, how do you feel about this?
Well, I think I agree that a quadratic speedup alone is probably not going to be competitive. I think that the way it could play a role is if it's part of the whole story. Like, let's say you're exponentially speeding up a quantum chemistry simulation, and then you want to later on top of that some sort of machine learning model. Like maybe you want to not just simulate a molecule, but search over a large family of molecules for one that has this property. Then you're doing two challenging things, and you hope that neither one contributes a crippling amount to your runtime. And I think the other answer is, I think we should our level of understanding is low enough now that it's still worth studying quadratic speedups, even if they're not going to, you know, be by themselves the reason why it's worth using quantum hardware, right? I think that we, you know, the field is transitioning from one where it's just like purely curiosity driven to one where people want practical impact. And, you know, it's great that we're now like looking for practical impact and trying to make these things have an economic return. But our like basic level of confusion about what's going on, you know, I think still justifies pursuing things that don't have immediate application, like, you know, contrived problems or more modest speedups, or, you know, anything that, you know, just things where sort of intellectually, like Marie was saying, you know, we can sharpen our swords on something where we like, if we learn something from it, then that's useful, because there's still quite a lot we don't know about the field, even if it's not going to be of immediate practical interest. And I want to respond to something that Ewan said. When you mentioned that these dequantized algorithms are not, you know, they have these runtimes, you look in the paper and it's like log n to the 8th power or something dire like that. Mm-hmm. The algorithms still contain very interesting algorithmic ideas, like taking a large matrix and approximating it by a subsampled one. You might be able to run these algorithms outside of the regime where the theoretical guarantee is going to work. Have you tried that? Have other people tried that? Or what do you think of that?
So yeah, there's some interesting, I guess one interesting paper that I know of that sort of discusses these sorts of subsampling tricks in the setting of doing like linear algebra, things like lowering approximations and things like this. And essentially the results that it gets is like, I mean, to get technical, I think that paper claims like a 10x speed up, but with 10x worse error or something like this.
Right.
So it's certainly things work. But the question is like, I guess what Maria is saying is like, does it being faster actually lead to interesting applications, even if you sort of forget the error issue? Like, for example, I think like the sort of like the recommendation systems problem that I guess there's been some focus in machine learning on, or quantum machine learning on quantum versions of this problem. And I've had people tell me that apparently the more pressing issue is just being accurate more so than actually being faster. I mean, certainly being faster is helpful if you want to like, you know, like being faster is helpful perhaps so you could spend more time trying to be accurate. But the issue is mostly on sort of the expressivity of your recommendation model, rather than any sort of speed up. Did that answer your question?
The poor scaling with precision is then a problem, even if they scale very well with the dimension. Yeah.
Yeah. Yeah, and I kind of wanted to build off of what you two were saying, which is that I feel like the question of speed up is sort of a question that's sort of well defined, and that makes it easy to sort of analyze theoretically. But but the whole sort of conceit of a speed up is that you have some classical machine learning pipeline, you have some classical input data and classical output data, and you have some piece of this pipeline that is like some classical machine learning algorithm, and what you would want to do is replace it with like some quantum machine learning algorithm and see whether it gets a speed up, right? Comparing the classical setting to the quantum setting. But this sort of ignores to some extent the possibility that, okay, maybe you don't want to run your quantum machine learning algorithm on classical data, you want to run it on quantum data. And in this case, it's sort of like you could sort of ask still, okay, how do I do a classical algorithm on quantum data? But this sort of question is, I guess, like sort of the question of speed up is different. Like there's not a more not as clear a notion of what you would mean by to have a speed up if your input data is quantum in the first place. And so sort of by talking about speedups in the first place, that we're sort of assuming some regime in which classical computers already have an advantage. And I'm not sure if that's necessarily what the goal for like near-term quantum machine learning is.
May I, or Kristen, unless you want to, because I already spoke. No, okay, cool. May I, because I also don't want to only be negative and say like, this is not happening, this is not happening. So may I maybe offer a different measure of advantage, maybe not even advantage, but something we should look out for. So, and I want to like tell you a little anecdote about this. So there's a question that like drove me nuts for a couple of years. And this is the question of what is the perceptron of, quantum computing? So in some sense, how can we make a quantum perceptron? And not only myself, because there are lots of papers, not really a whole kind of accepted version of it, but lots of different attempts of people who go and say, okay, perceptrons make neural networks are interesting, let's quantize a perceptron. Thousands of ideas of how to do it. It's very kind of unnatural to do it because there's dissipation going on, and this is not really nice for the quantum formalism. And then all these papers always have this section where they have to talk about speedups, and otherwise you don't get it through the referees, especially like, like whatever, 7 years back or something. So then they try to like figure out these speedups from these quantum perceptrons, and it doesn't really work. So this is the version that I would like to get away from, in my own head at least. And now the new version is the same question, but it has a completely different meaning for me. And this is, again, what is the perceptron of quantum computing? And now the perceptron, what I'm looking for is, again, this base model that enables us to do a lot of things. So for example, what's really beautiful about the perceptron is that it has very beautiful differentiation rules. So it enabled backpropagation, and backpropagation is arguably the one thing that makes neural networks so exciting, right? If neural networks wouldn't have efficient differentiation rules, then they wouldn't be here. And so, for example, instead of asking, what is my circuit ansatz so that I get a speed up, you could ask, what is a building block that's very natural for physics that has very, very nice differentiation rules, so we can just use it. So this is what I mean by forging tools. So now you've got that thing, no one knows if there's a speed up or if it's good for generalization, but we have these tools we can use now that have a completely different cost function of what we're trying to optimize in research. So I hope this gives a bit of an idea what I mean by this, the icing model or the perceptron of model building or so. And this is very exciting. This is not like boring. This is actually, in some sense, really, really cool work to do. But you have to get yourself a little bit of headspace from the commercial side of things, which is sometimes really hard. I mean, especially for if you want to work for a company or if you work for a company.
Nice. So this actually, leads to a nice discussion about something I was wondering, and Ewan also mentioned the difference of classical and quantum data. So then, what do you guys think is better suited or more natural? Is quantum data perhaps more natural, or data of a certain type classically could be more amenable to quantum machine learning approaches? So Kristen, since you have that very nice paper recently on this rigorous and robust speed up with a certain data set that you guys artificially generate for a specific problem, do you have some thoughts or ideas on what about quantum data and what is this interplay between the different types of data where we can maybe exploit something for an advantage with quantum machine learning? And you're on mute. Oh, okay, you're off mute. Okay, good.
Sorry. Can you explain a bit? When you talk about quantum data, are you thinking about data that is given to you in a quantum mechanical setting, or are you thinking in this context more? Are you asking more about data that comes from some quantum mechanical process, which is per se like classical data, but it's coming from a quantum process? So what is it that trying to sort that a bit?
Yeah. So I'm glad you asked that, because I should also ask you to explain what quantum data is, right? So to me, I wouldn't even know that there was a difference between the two things you just said. So and I think the general public will probably also not really be aware of what is even the difference between classical and quantum data and the distinction you just made. So maybe you can say something about that and then pick whichever one you would like to say something about.
Right. So I mean, I think probably the experts on how data is delivered would probably be Yuan Tang, who had this very nice dequantization paper. So maybe she would like to chime in on her perception of that. That might be very interesting. But from my perception, so I would call the latter, where you say you have a quantum process that produces classical data, still sort of classical data in the end, right? Because it's classical data that you read, it's classical data that goes into a machine learning model, and now you could maybe exploit some insight that you know of the process that generated that data to sort of do something meaningful in the quantum machine learning end. But the apparently very powerful thing, and what people often think about essentially in terms of quantum data, is exactly that data is given to you in form of a quantum state that is sort of not accessibly classically, right? And so that's where I would draw the distinction. But maybe Ewan has a much better perception on that. Maybe she would like to comment on that.
Yeah, so I guess like, okay, so I guess the difference between the quantum data we were discussing is like data that is given to you like on a hard drive or something, on a normal hard drive, but it comes from, you know, like some quantum system that you have in the lab somewhere else, or whether you're actually in your quantum computer, you're sort of simulating some quantum system, and then because like at the end of that simulation, you get some quantum state that you can then perform a machine learning on. Like it's sort of whether your input data is classical or quantum. And I think that when I was talking about quantum data, I was definitely referring to the latter one, where you sort of simulate a quantum system inside your quantum computer and then take that output and then do some machine learning on it. And this sort of makes sense to me because as Maria mentioned, when you get your hard drive of data in this other sense of quantum data, you still have to load it into your quantum computer, and that still takes linear time. So you've essentially, you know, like you have a lot of loss in potential like speed or like speed up right there. But certainly like, and certainly you also lose in some sense the, I guess, some information about the input quantum state when you're making, even when you make so many classical measurements, it's still you're sort of losing all of the power by converting it back to classical data. So I mean, the stuff that I work on is sort of quantum linear algebra. It's like sort of if you take input quantum states and sort of manipulate them, whether you can like sort of how these manipulations compare to doing the similar manipulations in the classical computer. And what I can say is that like, okay, if you have some quantum states, but you give me like a classical description of these quantum states, then I can sort of do similar things in the sense of like I can do sort of regression and things like this, and PCA and just basic like linear algebraic things. However, if I don't have that classical description, I can't do anything. And so essentially what it comes down to is that like as of the current state of like provable sort of the current understanding of like provable speedups in machine learning, it's sort of the case that if you sort of are trying to simulate if you're running quantum machine learning on a quantum system, if you're simulating a quantum system in your quantum computer, then we don't know anything that you could do sort of classically that even comes close to matching the sort of performance in terms of both like, I mean, we can't say anything about how high quality the results will be, or we can't say much because we don't have quantum computers, but certainly there's no comparable algorithm that sort of matches the bounds that we know of in terms of runtime and things like this.
If I may say something, I hope my internet is fine now, but actually whenever I hear people speaking about quantum data, so it's always like a discussion about, you know, classical and quantum, and then always it's like quantum data is the solution. And I'm just like wondering if we actually need a lot of research in that, where we have domain experts from those quantum experiments. So in other words, we have to get some experimentalists like into our midst and say like someone who knows exactly what these states are and what you want to do with them. And then, you know, just like to merge. So maybe there's really a gap of just good research. I mean, we start seeing a lot of like very theoretical high level stuff, but I mean, really like in the mud, you know, with your gumboots and see if you can say something about concrete cases.
Yeah, I definitely think that like the reason that I guess like sort of what sort of my place in the quantum machine learning literature is just purely because like it exists just because I can prove like these theoretical bounds. But I don't know if I could say anything about anything concrete in terms of what actual thing that you could do with like quantum machine learning, because as you said, you would need to actually get down into the sort of into the mud and discuss what you would actually want to do for some quantum system that's like real and experimentalists care about. So I agree with what you said.
Speaking about,
there's been some.
Okay.
Oh, good.
No. Please go for it. Yeah, I'll ask you after.
Yeah, I guess some part of what we might be seeing is there's a gulf between like the theory describes what you could do with a pretty sophisticated quantum computer, and then the experiments describe what you can do with today's system. And in the quantum sensing, you could say quantum sensing is one version of this quantum machine learning with quantum data, right? And people who look at nitrogen vacancy centers and also chains of trapped ions or neutral atoms, they've been doing increasingly sophisticated things with trying to improve the precision of quantum sensing. I don't know if you'd call it machine learning because it's sort of a well-characterized enough system that you know what you're measuring, but it does use entanglement and quantum coherence to better get a signal out of the quantum data that you're getting. And yeah, I agree that you definitely need a lot of domain expertise for these because as quantum computer scientists, we're used to talking about universal quantum computers, right? And these are very much non-universal, and that's part of the point, is that usually there's some part that we haven't characterized, like the NV centers fall at random, or the magnetic field we're trying to sense is an unknown field. But yeah, I think there's a lot of room for using quantum computing ideas to improve these physics experiments. And then I think also this question of classical or quantum data. I mean, of course, the answer is both, right? Like we want to use quantum computing to improve all these things. We want to use quantum computing ideas to take advantage of coherence to improve these physics experiments. But we also hope that if there's some classical machine learning problem that has to do with data from genomics or something, hopefully we have something to say there too, right? So I don't think we have to choose. And certainly the application to the physics experiments is the more certain one, but we should also be trying for these more speculative ones where there's a large classical data set, which is not necessarily well adapted to quantum computers, where there's also sophisticated classical competitors. Even though that makes it an uphill battle, I think there's wherever there's a hard computational problem, we should try for quantum speed up there too. And I agree with Maria, we can look at quantum techniques without them having a speed up, but ultimately we want there to be a speed up at the end of the day. Sorry, Amira, you were saying?
No, I'm that's fine. And I don't know if you want to retaliate, Maria, because I know you feel very strongly about. Okay, that's fine.
No, I really. Yeah. Oh, wait 1 second though. Oh yeah. Sure. So maybe also just for people, because that took myself like many years to really figure out what is actually, when is something then machine learning and when is it not. So I was just like thinking about the quantum sensing one. I would personally say, but that's an opinion. So the moment you have got data and what you want to do is generalize from a data sample. I think this is the essence of machine learning, is like you have samples and finite sample approximations. You want them to be good on other samples that you could sample from the same distribution. So I'm just like wondering, it would be nice to go out and see if we actually have automatic, like already these problems in physics, but it's not so super obvious, right? Like it's not what we learn in physics 101 is immediately like a generalization problem. So that could be very interesting to find.
Yeah, some people have talked about learning quantum phases, which is sort of blurry because we do have a lot of prior knowledge, but maybe we don't fully, no. But yeah, it's a good point that some of these things don't have the generalization feature of machine learning.
So Aram, I want to ask. Okay, so actually the whole panel, but we'll start with Aram. So I want to ask one more technical question, and then I think I think we should discuss things a little bit more generally, because yes, most of the students are also dying to know things like, you know, advice from you guys, from successful researchers in the field, so we can get to that after. But something I was wondering, and I'd love to hear, you know, all of your thoughts about this. So so many, I think Maria actually alluded to this in something that she said earlier. So many like known quantum algorithms that are good, like cleverly use the structure of a certain problem, like in factoring. And so what makes us believe that in learning and in machine learning, like there is where there's often, you know, not this kind of structure, that we can get these quantum speed ups or advantages. So yeah.
Yeah, that's a really important question. And you know, I would say we don't know if we believe that. Like we believe that there are very generally you can get a quadratic speed up. That's very. If you ask me about a problem I haven't heard of before, I think there's a very good chance you have a quadratic speed up for it. We know in some cases they're beyond quantum speedups, even for sometimes kind of generic things. Like I really like Tong-Ying Lee's and his co-authors' recent work that says you can escape a saddle point in some kind of wacky optimization landscape cubically faster than with stochastic gradient descent. So that's a you know, a generally important problem with a more than quadratic speed up. Maybe more of these things exist out there. I think that's very plausible. Yeah, but and you know, we're looking for them, but we haven't disproven them, nor have we found tons of them. I don't think. Yeah, it's hard to say with great confidence more than that. But I wonder what other people's perspectives are.
Yeah, me too. Anyone want to jump in? No one. I'm going to pick someone then. Kristen, you're on mute again. Yeah.
Yes. So I don't think I have a lot more to add other than what Aram says, because the end, I agree with the statement that mostly what we're looking for are structure problems, because then we can say something, right? It doesn't necessarily mean that that there aren't other problems out there that you could find by trying and so forth, but we're just sort of confined or have the urge to actually be able to say something concrete, which is sort of like reliable in that end, right? And so for that end, I don't know whether that's probably the main reason why we care a lot about structure at the moment. I would say going forward, I don't know.
Okay, perfect. Thanks a lot for your opinions. Okay, so maybe we can shift a little bit to some more broader and general questions about the field of quantum machine learning, because a lot of our participants of the school are new to the field, are new to quantum computing, and very excited about it. So also, you know, what advice would you give someone like this starting out in the field and specifically very excited about quantum machine learning? So maybe we can start with Maria, and each of you could just give some thoughts about, you know, how to get into the field successfully, and what does that even mean, and and remember that, you know, people are different with different ideas, different backgrounds. So.
I want a bit of time. No, I'm joking. So I really love about quantum machine learning for beginners, even more than quantum computing. So although they're probably on par by now, but like that, there is just so much software out, and the software teaches you so much. So this playing around factor is obviously really nice. And usually the people who write the software are very, very interested in community building. So the companies spend a lot of money on people who just build community, and it's a whole like business. So if you have questions, it's actually up to the development team. They're often like very open to answering them. So there's a very cool, transparent structure in that. That's cool for beginners. I think that actually to contribute meaningfully to research, what you need is a good advisor in the sense. So doesn't mean you have to go into a group of someone who's super famous for quantum machine learning. I think you just need an advisor who is very critical and has this overview of research and understands how to, you know, select what's important and what's not. And then that will help you to find the right places. And then the last thing is this courage to do critical thinking. So for example, I get a lot of questions of people who do the following. They say, like, I've trained a variation of circuits on cancer data and stuff. And then I found, like, you know, if I switch on this entangler, something happens in my generalization error in my experiments. But so what? And then the students are super confused about this because they don't know really where to go from here. And you know, maybe if you look at it critically, you can say, like, actually, my research question is not really well defined, or I'm, you know, the goal, I'm just like running behind the trend and trying to do what our other papers do, but maybe I'm really interested in finding out something completely different about the problem. So in these moments, I think one needs a bit of courage to drop what everyone else is doing and then, you know, find this question that you're really interested in and go really deep into that, even if reviewers, you know, want to hear other things, and then just do that. So, okay, that was a little bit lame, but I can say for my own life, at least, whenever I did do one thing and not the other, only because I was interested, it has never ever been a problem and always paid out. And I assume this is true for most researchers. So
awesome. No, we always appreciate your honesty. And
well, it has been a long time. I must say also, like, so sorry, when Amira, I was thinking, because so yeah, Amira and I meet every now and then because I'm actually a supervisor as well, or well, friend and supervisor, but I start also realizing you lose connection to how it was to start. I remember it was really, really hard, but I lose connection to this feeling of what people know a couple of years ago. So it's kind of, maybe actually ask the people who are just a year or two above you and not also like us old farts. It might be a better idea. Okay.
okay. Yeah, thanks. No, but I think you gave a pretty good answer, and that was really good advice. And yeah, and you're not an old fart, very far from it. So yeah, I don't know. Maybe we can hear from Ewan, because you know, I think your perspective is also very unique and probably very different, right? So I don't know. I think the question was that roughly, like, what advice would you give to someone, you know, starting out in quantum machine learning and wanting to get into it, is very excited about it.
I would echo the being critical comment. I mean, I think there are a lot of good and equally valid ways to get into quantum machine learning. Like, I think so certainly, like, I guess there's ways to get into it starting from, I guess, a software engineering perspective. I came in from like a math and theoretical computer science perspective. I have never taken a quantum physics course or anything. And, you know, obviously you can also get into quantum machine learning via like knowledge of like physics and quantum physics. So I think, I mean, I think there's like systems and support networks like this Qiskit stuff, this school that is like really good mechanisms for sort of becoming aware of like this field from like a variety of entryways. And I think I don't necessarily have advice beyond that, because I think my my particular circumstances were a little bit special. And I definitely was like came in from I guess was privileged to work with the people that I worked with. But I mean, there's definitely major gaps in my knowledge, but that I like learn to try to fill every day. But I think it's just, I mean, it's not that important, as long as ultimately the things that I do are I know about those things, which is, you know, there's a lot of areas in quantum machine learning to investigate.
Yeah, and I think that's actually so nice to highlight, right, that even these experts and people in the field who are very experienced are still continuing to learn, right? So that's also important, to just always be open to keep on developing and furthering yourself. So yeah. Okay, so maybe we can hear from Kristen next on, you know, your advice for a quantum machine learning beginner.
There's a point that both Maria and Ewan basically mentioned, and that there is what makes it interesting, that there's various different levels on how you would like to engage with this, and how you would like to develop in this, right? So what came out is basically that a nice thing is exactly because you have software available. There are many courses like this one available. Other things are available. And there is a community available, so that there's depending on what your personal preference is, there's various ways to go about that. And I think that's a very nice feature right now of where the field is at the moment. And in terms of advice, so it depends on, I guess it depends on where you personally are as well, right? So there may be people that have a strong software background, and so then it's probably not a good advice for someone that's there. Oh yeah, well all you have to do is now you have to redo all physics courses and then go into grad school and then finish that and so forth. Although that is also very good advice, very important advice depending on where you enter. But sort of yeah, I think it's sort of, it's interesting that you now that there is the chance to actually have a community that you can fall back on and actually find sort of a way that suits you most, essentially in figuring out where you want to go and what it is that interests you, right? So
beautiful. Yeah, thank you. And Aram, if you want to add.
Yeah, so the other three did a really good job. One thing that Maria said I might build on a little bit is she's talking about being, critical of your model, saying, is this really like the best, this works, but could a simpler one have done it? And of course, that's also true for classical models, right? If you get a neural network to work, you should say, well, could linear regression have done the job, right? You should always do this. And one thing I found related to this, really helpful in my own career, has been, it's been surprisingly productive for me to keep chewing on the same problem. So I'll look at a problem, I'll study it, I'll get some results, I'll be happy about them, and then I'll go on and do other things. And then I just keep coming back. And I find that sometimes if you have there's some loose thread, I was like, I didn't quite understand that part, or this part, I understood this, but I didn't know why I was acting like that. And sometimes it can be really productive to just keep deepening your understanding of even something that seems pretty simple. If there's any loose thread, if you feel like there's any piece that you don't get, that can be very useful to just keep on chewing on something and getting more and more out of it. And the other thing I would recommend for people who are coming into this field, of course, from all different backgrounds, is it's good that you can just get your hands dirty and just get started and try to, but as you go along, you don't have to take the quantum physics class right away, but you should also not be afraid of quantum physics. As you get started, don't think to yourself, well, I'm a computer scientist, I'm not going to learn physics, or vice versa, because one thing about quantum mechanics is that it traditionally takes a very long time to learn. But I think, and many other people think this too, that if you learn about qubits first, it actually makes it much easier, and that it's actually a much conceptually cleaner way of entering into the quantum physics curriculum than the traditional way. So you may find that if you spend your time around qubits, then traditional quantum mechanics is actually much easier to learn. And in general, you can come from many different backgrounds, but eventually it's worthwhile to be what they call multilingual, right? When you speak the different disciplinary languages, eventually that can be a useful thing.
Can I add one thing that I totally forgot? It should be actually the number one thing is don't be scared of machine learning, because
right.
So at least from our own experience, for many years, I always thought a little I don't know why, but I didn't really read machine learning papers, because everyone always reiterates this thing of machine learning doesn't have theory and it's just practical and this and that, and then you read the textbooks and get the algorithm, it's fine. But machine learning theory is one of the most beautiful things in the entire world. It's super involved, and they have exactly those, maybe this is why I'm so inspired by them, but they have these models that I'm talking about. So where you have kind of a linear model that can give you so much theory, can tell you what double descent curves appear in generalization, and you can really start playing around with these things. And they have all these tools. They have very interesting questions, very clever researchers, easily written papers, so you can read them, actually, most of them, if it's not too statistical, actually. But I think if you are really interested in quantum machine learning, in most places in quantum machine learning, I think you should read as many machine learning papers as you read quantum papers. And I don't think many of us do that, including myself. So.
Yeah, I couldn't agree more. And yes, I think also, just to reiterate, Aram, what you said about starting with qubits and quantum computing, first to get into quantum mechanics. Yeah, 100% agree. I think I was terrified about physics in general, because I'm also not, not a physicist by background, and quantum computing definitely made it a lot more digestible to enter the field. And
Good.
I think a lot of people, I think a lot of people are seeing that hopefully now after this 2 weeks summer school as well. So there's just like one more question that's coming up quite a lot in the chat, and I don't want to ask it directly. I want to like rephrase it. So everybody is asking, how do I find a mentor? How do I find a good mentor in quantum computing, quantum machine learning? But instead of asking you that question, maybe if you guys mind sharing a story about how you, I'm sure everybody here has had a prolific mentor in their lives that's really helped them, get into the field or do good research or something like this. So maybe you can chat about how you got this person or this mentor, because it might shed light on how somebody else can find a mentor in the field. So if anybody would like to, volunteer to start, because I'm always very passionate about speaking about my mentor, who is here in the chat, but I'm sure everybody is tired of hearing that story. So yeah, perhaps we can start with Aram if you want to go first.
Yeah. So I don't know how generalizable my story is, but basically I was an undergrad, and I didn't know what I wanted to do. I liked physics, math, and computer science, so I thought this might blend all of them. And I approached Neil Gershenfeld, a professor who did some very early NMR quantum computing experiments, and I was advised that he was very busy and I should approach his grad students instead of him directly. And I was an undergrad, I talked to his grad student. The grad student was very nice, a good friend of now. And then I talked to Neil. Neil gave me some problem. I went away and worked on it and presented to him. And then he took me on in his lab, and I did really bad experimental work, but had a lot of fun. And then Neil introduced me to my grad school advisor, who was Ike Chuang. Ike introduced me to the group at IBM, where I did my summers and had a really good time. He also, it was basically a lot of introductions after that. So it was, I guess, my story is really just that I met people and worked with them, and they recommended me to other people. So
but that's still super important, right? I mean, that's the point. I think you made the initiative, and it all starts with people. I think a lot of people forget that, it's people that make things happen for other people. So that's, I think, really crucial, right? And reaching out, and then you find the right people just by putting yourself out there and asking, and that's exactly what you did. So I think it is relatable. Yeah. Awesome. Okay. Anyone else want to tell us about their mentorship stories?
I can go next. But it's so funny it's so nice when you ask questions, people always like give general answers, then you ask them about their story and they tell you, it was not typical, but okay, so I think also my story often told, but not very typical. I actually wanted to study political science, and I did physics out of like various reasons, like at the side for a long time. And then I finished my master's in physics. Then I finished my master's in political science. Then I wanted to apply for jobs in political science, and I didn't find a good job. Basically, I failed assessment centers, and like it was absolutely horrendous. In the meantime, I emigrated to South Africa, so this was also maybe a bit of a part of it. And then I thought, okay, let's do a PhD. Also here in Durban. So the important thing about the PhD was basically where it was for me, and I wasn't, even caring about any topic or something. It was more an unemployment avoidance campaign. No, I also wanted to do a PhD, but anyways. And so that kind of gave me the freedom to do whatever I wanted, because I never wanted to be a physicist. And here's now the crucial part. So that I always tell, so I also get a lot of emails of people asking, like, so where do I find the supervisor in QML? That's why I mentioned this earlier. And so at least for me, there was not a person who had any knowledge of the things that I was doing. This is always helping. Yeah, it's always nice. But like, people are often very busy anyways. But I had a supervisor, so Francesco Petruccione, who gave me support in money. So he sent me to all conferences. So even in masters, I didn't even have half a paper, and he was just sending us to conferences like all the time. So the connections were made then. And support me just like being nice and being like, you know, just being there and standing up for my shit, and even if I had weird research topics. So my personal experience is that if you have someone who supports you on all the human levels and the financial level, which I think is really important, the traveling, so someone who sends you out and lets you represent your own work, I think that the rest you can get from mentors that you get through programs. I don't know if others would agree to that. And so maybe for you guys out there who are also not at MIT and Caltech and have the, you know, the Ivy League networks that are strong and they are wonderful, you can do it. I mean, Amira and I are both at the University of KwaZulu-Natal. I don't know if you've heard of this place before, but if you have the right people around you, it doesn't matter. You've got internet connection and this funds for travel. That's actually enough if you are very motivated and if, you know, like you have the will to actually go through with that. So
yeah, and you don't have to have strong internet connection, right? Because Maria, we can't even see your video right now, but at least we hear you, and it's very motivational.
See, it's working without internet connection. Yeah.
No, that's beautiful. Thank you so much for that. I don't know. Okay, so we have two more to just offer your mentorship stories, Kristen and Ewan. Yeah, Kristen, you want to go first, or?
So for me, I mean, I did a classic undergrad in physics essentially before I went out to look for a PhD. But that was actually for me was actually very complicated to find a good PhD advisor or environment to do it. And so I actually had one failed attempt of a PhD in physics before I switched over into quantum computing. And the mentor that really worked for me was then Frank Verstraete, who I found. And I basically found him when he was really just starting out as a supervisor. So actually I presumably among his first grad students that he had. So that was fun and something where what made me very interested in trying to work with him was basically exactly that. In that setting, it was mostly I've spoken to a lot of people before and looking for supervisors, and I had some supervisors which exactly told me, look, what you have to do is you have to pick this topic, you have to go this way, and this is your development. And whereas with Frank, it was really a lot more. So what is that you want to do? Sure, I don't know about this, but I can help you figure it out and work in that direction. So that was something that really worked for me in the end. And so that was actually a fun relationship at the beginning. Yeah.
Awesome. Thanks, Kristen. Ewan, do you want to go next?
Yeah, sure. I don't necessarily have the benefit of hindsight because I'm still doing my PhD. But I guess I can discuss like what happened in undergrad, which is that like I was pretty directionless in terms of like what I wanted to do. I started off doing like doing math, and then I sort of switched over to theoretical computer science after a friend was like, you should do theoretical computer science. And then I sort of fell into like quantum because somebody told me, hey, there's this new professor, Scott Aronson at UT Austin, who was doing some cool work in quantum computing. And so I took his course, and then it sort of led into me asking him, hey, like, can I do a project with you? And he introduced me to like quantum machine learning. And so there's, I guess, in this way, sort of, I was able to like get some direction about what I sort of like the research that's like interesting. And in fact, like most of that work that sort of was sort of the jumping off point for the line of research that I'm currently working on was actually done while he was on sabbatical. So I actually didn't get that much interaction with him sort of at all. And mostly spent time talking to a couple of his grad students. And that was extremely helpful, just having an environment where I could go into a space and then people were thinking or talking about quantum computing, and I could be like, hey, I'm looking at this paper. Can you like just like look at this paper with me? And just have a space where that was an option. And sort of from there, you know, after I sort of got this result, Scott was very useful in sort of spreading my name around, I guess. And I think I got a lot of benefit out of the sort of connections that I was able to foster as a result of having him sort of advise me. and sort of as Aram said, since then it's been just sort of knowing people through knowing people, and so that's sort of how I got started.
Awesome. No, that's super cool. Yeah.
I actually add one quick thing about what was really helpful for me early on, which was, so I did go to MIT for grad school, which now has a ton of quantum computing people. At the time, it didn't have so many. And I think that was actually really helpful to me when I would go to a conference that I would know nobody there, or I would know them only by reputation. I would know them only by their papers. Of course, the field was a lot smaller then. But that was really helpful to me because I would walk into someone, I would see their name tag, and out of like awkwardness, I would try to find something in common between like my limited research and what they had done. And that was, I think, very, in the long run, very, very, very good for me to like be able to make these scientific connections to a lot of people. And now that the field is so big, it's very easy to go to a conference and there are 10 other people from your institution there, and you can just have lunch with them and hang out with them in the evening and not meet that many new people. So I think it was very helpful for me to be in situations where I didn't know anyone and I was awkward and I was going to have dinner by myself unless I like went out and like, got to talking to people I'd never met before. So yeah, I recommend trying to find yourself in that situation, which of course gets harder as you get to know more people. But in the early days, it's actually a good thing, good place to be in.
Yeah, and hopefully once the world starts to normalize again and we start having in-person events and conferences, then yeah, we can start to do this. So thanks to all of you for your stories. It was really quite wonderful. I'm sure a lot of people will find that very useful, very motivational. And since we just have a couple of minutes left, I just want to ask you a little bit of a sci-fi futuristic kind of question, and we can end off with something fun. So maybe we can do it alphabetically. So we start with Aram and we work our way through. So okay, so imagine we're like 50 years into the future and we have beautiful fault-tolerant quantum computers available to us. What would be the first thing that you would do with a quantum machine learning algorithm or technique or application? Like, what would be like your go-to thing that you want to just immediately answer about quantum machine learning if you have access to a fault-tolerant quantum computer?
Good question. The first thing I want to do with a quantum computer is I want to simulate some hard quantum systems. I want to know what happens with catalysts. What does the middle of a neutron star look like? Can I model a high temperature superconductor? And if I were, then I might try to layer machine learning on top of that. If I have a bunch of different if I have my dream quantum computer that can, let's say, figure out based on the chemical formula, is this thing going to superconduct or not, and at what temperature, then I might use that to try to make a classifier that would predict that for future things, and maybe try to figure out some pattern there. So this is maybe a bit of a cop-out because I don't know how much of the important part of that would be the quantum machine learning part of that. I think machine learning would be a part of it, classical or quantum, but definitely the quantum modeling of physical systems would be an important way of learning new things.
Awesome. Ewan?
I'm gonna be honest. I don't know. I think my vision, it would be probably similar to Aram's, except in this situation I wouldn't be doing the experiments. I would just be reading about other people doing the experiments and sort of being happy that this field of quantum machine learning turned out to generate some useful scientific insights. I don't know if I could do it myself.
Okay, cool. Okay, who's next alphabetically? J, K, K, L, M. Okay, Kristen.
Yeah, so, I mean, there's many things one would want to try in general, I suppose, once you have a universal fault-tolerant quantum computer, which are not necessarily immediately machine learning. But if you specifically ask about machine learning things, what is sort of interesting is that over the last couple of years, and maybe you could probably assume that going forward, that there's sort of a trend that a lot of nice and neat ideas are being proposed in terms of heuristics, which are exactly falling into to the line of where you say, you don't know whether they actually do anything better than what you would have already. And I would be just curious and trying to find out how many ideas actually survive and whether you find something out of the heuristics that are being proposed. That's probably the first thing I would be interested in seeing happen on a functioning quantum computer at large scale or something. Because yeah, to try a lot of those things, yeah, you have to just sort of be able to go large in that sense. Right. So that was something I find very interesting to see.
Okay, cool. And yes, last but not least, Maria, if you can still hear us, right?
I think yes. Sorry, as my video, I see you guys fine. Anyways, for me, it's quite simple. So first I would take a selfie and then I would send it to my grandchildren and absolutely brag about like what I was involved in. They would probably not even care. And then I would build probably a time machine, go back in time, then tell myself that it will all go out, like end well. And then I will tell myself not to tell anyone else how it's built so that they don't miss the fun of building it.
Okay, sci-fi answer for a sci-fi question. Thanks a lot for that, Joe. Okay, cool. So yeah, I don't know if anybody else has any closing remarks before I thank you, but yes, no, last thing. Okay. So yes, thank you all so much for having this discussion and this panel. And I think it will be really beneficial for those watching and for those who just spent especially 2 weeks learning about quantum machine learning and the basics, and to hear, you know, your opinions, your thoughts about the field, how to get into it, mentorship, and even the technical details about, you know, where the promising applications are and this whole idea of speed ups and you know, what we should be looking for. And I think this is really quite amazing. And I just personally want to also thank each and every one of you for agreeing and giving us your time. And I really enjoyed chatting with you. And thank you so much. Cool. Then I will, yes, no, of course. Maybe we'll do it again next year. So let's see. And then, yes, thanks everybody for the summer school, attending, watching today's panel, and just being a part of this whole quantum machine learning community. So we look forward to engaging with you at future events. So take care.